Hey everyone, welcome to lecture 2, and we're going to start off talking about paramagnetism and diamagnetism, which really kind of follows our idea of our atomic Lewis dot structure. So let's take a look at what these two terms mean. So paramagnetism has to do with how an atom interacts with an external magnetic field. And for paramagnetism, if something is paramagnetic, it means that that atom or ion is attracted to an external magnetic field. Let's take a look at something like a silver atom. So if we look at silver, we see its electron configuration is krypton 5s1 4d10. Okay, the electron configuration itself does not necessarily tell us if we are going to have paramagnetic or diamagnetic. So we really need to look at the orbital diagram. And there we see that we have an unpaired electron there in the 5s. So anytime that we have an unpaired electron in our atom, so we see that unpaired electron in the electron configuration or in the orbital diagram like that, the atom will be paramagnetic and it will be attracted to an external magnetic field. Let's look at an example of something that is diamagnetic. Okay, so if something is diamagnetic, it means that all of the electrons are paired. And this is where it gets a little confusing. I know when I was in your shoes many years ago, that used to confuse me because para sounds like paired, but paramagnetic means that they're unpaired. So I recommend remembering that diamagnetism, di means two is a pair, and so diamagnetism means that all of your electrons in your electron configuration are paired. So when you have something where all the electrons are paired, then that atom or ion has no attraction at all to an external magnetic field. Let's take a look at two examples, a zinc atom and a zinc ion, to see if there's any difference between the two as far as their magnetism. If we look at a zinc atom, it has an electron configuration of argon 4s2 3d10. We see that all of those electrons are paired up. Let me just change some things here. So we've got our pair right here, and we've got all of our pairs here. So every single atom or every single electron in that electron configuration is paired. Therefore, a zinc atom will be diamagnetic. Now, if we go to a zinc ion, we take two electrons away. And this slide actually shows two very important points. One linked directly to our magnetism and one linked to the idea of electron configurations of ions. So as far as the magnetism is concerned, we see that we actually lost our 4s electrons first. We formed a zinc 2+, and we had to take away 2 electrons from a zinc atom to form a zinc 2+ ion. Okay, and then you'll notice that we've got all pairs there in the 3D, so it's still a 3d10. Now, when we're writing our electron configurations, we fill in the 3D electrons after we fill in the 4s. Okay, but when we are taking electrons out, we always take them out of the highest n level first, so that highest principal quantum number first. And the reason for that is once electrons begin to go into that 3D orbital, its energy drops, and it drops below that of the 4s. And so the 4s, once you have electrons in the 3D, the 4s becomes your highest energy orbital. You can still put more electrons into the 3D. It's the lowest energy orbital available, so that's where the electrons go. But when they come back out, they come out of the 4s first. And this is true for pretty much all of the transition metals. There are a lot of weird little things that happen with the transition metals and their electron configurations. We're not going to worry about those in this course. If you go on to take inorganic chemistry, you'll see them there. But anyways, so our zinc atom, diamagnetic, our zinc ion, also diamagnetic. And the fact that it's diamagnetic tells us that those electrons came out of the 4s, because if they had come out of the 3D, then we would be missing that electron and we'd be missing that electron, and we would have seen paramagnetism instead of diamagnetism.